All right, well, up until now, we've been looking at built-in facilities in Python. Now we're going to take a look at Numpy, which is one of many add-on modules for Python developed to do data analysis and data storage and manipulation and so on. Numpy enables you to handle n-dimensional arrays of values. It has built-in so-called vectorized math functions that operate on these values in a very efficient way. It also provides linear algebra functionality and a variety of other things. Unfortunately, a lot of which we're not going to have time to get into. Then next week we're going to introduce Pandas, which gives you the ability to describe things like time series and also to create and interact with what are called data frames, which is sort of spreadsheet-like collections of data. And some other very commonly used modules for things like statistics and scientific calculations and so on include things like SciPy and stats models, and et cetera, et cetera. Now, there are standard abbreviation conventions for these various widely used modules, libraries, whichever. And for NumPy, almost always people use the abbreviation NP. In fact, if you look at books about Python and including NumPy, usually the examples will use the abbreviation NP without necessarily even showing how that was set up. Likewise, we're going to be using PD for pandas. Okay, so we know that when we create a list by saying something like M gets 1, 2, 3, 4, 5, whatever, that the list contains that sequence of values, and we can access the items in that list by using subscripts 0 up through n-1, where n is the size of the, or the length of the list. Okay, so m sub 4 is the last item here. Now, although we think of a list as containing a sequence of items, in fact, in memory, these items can be all over the place. There's no guarantee that m sub 0 is located in memory anywhere near m sub 1, which may be nowhere near m sub 2, and so on. Now, what an ND array guarantees is that all of the elements in an ND array, sorry, I didn't define ND array, the NumPy ND array, which is the n-dimensional array that the NumPy module defines, guarantees that items within the ND array are in contiguous memory. And this turns out to be a much more efficient way of storing information and supports the idea of vectorized computations, which are highly efficient. Okay, so here we have ls1 is a list using the iterable range 5. So ls1 refers to a list containing 0, 1, 2, 3, 4. To create an analogous ND array called A1, we would say, whoops, I just realized I had told you that we were going to use the conventional abbreviation NP for NumPy, but I'd better actually do that. So let's import NumPy as NP before we try to use NP. And this is not a small module. It takes a little bit of time to load. There we go. So finally it's loaded. So now I'm going to create A1 to refer to NP dot. Now A range is NumPy's analog to the range iterable. It creates an ND array based on a range of integer values, starting by default from 0 and going up to but not including the value that I've given as the argument here, 5. So here is what A1 displays as. It has the same sequence of values, 0 through 4, that the ls1 does. Now, To access items in a list, we know that we can use square brackets with subscripts starting from 0. The same thing is true in A1. A1 sub 2 will be the 2. I probably should have chosen a more interesting sequence of values for A1. And just like with lists, I can use negative subscripts to count from the end of the array. So A1 sub -1 is the last item in the array. A1 sub -5 is the first item. And as with the list, if I go out of bounds, I'm going to get yelled at. So A1 sub 5 in a positive direction is outside the ND array. Okay, now in Python, the int data type has arbitrary precision. We can have integers that are as large as we can possibly contain within memory and that we're patient enough to wait to display on our screen. But for efficiency, ND arrays have much more restrictive sizes for integer values. What we're using here with this ND array is what's called 32-bit integers, corresponding to the int data type that you would find in C or C++ or Java. Consequently, if I ask for the type of a list item, ls1 sub 0, I get told that's a Python int, but if I ask for the type of a1 sub 0, the ND array's integer data type, I get told that this is a Numpy int 32. All right, so whereas I can say something like ls1 sub 0 gets 1234 to the 1234th power with no problem. I mean, that's a huge number that's going to whip off the top of the screen here. Well, okay, so 50 lines squeezed. We'll trust that that's a big number. But if I try to do the same thing for A1 sub 0, I'm going to get an overflow problem. Now I can do, whoops. On the right side of the assignment here, this is a Python int, and this is a Python int, and so I can do a Python int to the power of a Python int and get a huge Python integer value as a result. But when I then attempt to assign that into A1 sub 0, it's going to be too big to fit. And so I get told that the Python int is too large to convert to a C long. Now, all right, if you're a Python programmer, you're not obliged to know what a C long is. But in the C language, a long integer is typically a 32-bit integer on most systems. Okie doke. So the largest value that you can fit, just so you know, into A1 sub 0 is 2 to the 31st power minus 1. Okay, so the largest positive value is 2 to the 31st power minus 1. The largest negative value is the negative of 2 to the 31st power, which takes up all 32 bits of binary digits that we have in the integer. So here is the maximum positive integer value that you can have that will fit within an ND array numpy.int32. Okay, now an ND array is iterable. Consequently, it's easy to convert ND arrays to lists or tuples or sets just by using their construction functions. All right, here's A1. Whoops. Let me restore A1 sub 0 to just plain old 0. All right, so there's A1, and if I want to get a list from this, I can just say list from A1, or a tuple from this, I can say tuple from A1. Likewise, a set, I can say set from A1. And of course, I can loop through A1. I can say for val in A1, print val. So an ND array is an iterable and can be used any place that an iterable can be used. Now, what we used to create A1 was a range. Let me go back up and find that. So here's where we created A1. We said nparray.arange and just gave the one past the upper end of the range of values that we wanted. To create an array of arbitrary values, instead of arange, you use the array construction function with some arbitrary iterable. So I can say things like A2 gets np.array and then give a list, which is certainly iterable. 3, 4, 5, 6. And now I have that NumPy array. In this next example, I'm creating a NumPy ND array from a tuple of 2 values. Okay, so there's my open parenthesis for my function call, and here's an open parenthesis to create a tuple, 1, 4, 1, 5, 9. So I've got pi and e to just 5 digits of precision. Okay. The second one that we created here, A3, is not integer values. The values in A3 are floating point. And specifically, the type of these floating point values is numpy.float64. Well, it turns out that that 64-bit floating point type, which in the C or C++ or Java languages would be called double precision, is exactly the same size as the standard Python float type. So it does turn out that you can take any valid Python float and store that into a NumPy float, and vice versa. They occupy exactly the same range and magnitudes of values, and they have the same bit patterns within the 64-bit representation. Now, a list can contain items of arbitrary data types. You can have a list of mixed integers and floating point and Boolean and string and so on. However, in an ND array, again, this is for efficiency to make sure that memory is being used in a very compact and efficient way. All of the items within an ND array have to be the same data type. And if you attempt to create an ND array object, here I'm creating the variable A4 to refer to an ND array object. I'm attempting to create this ND array object by giving an integer as the first value, then a float, then an int, and then another float. And rather than giving me an error for trying to do this, what NumPy does is to do what's called upcasting the simpler data type values into the more complex data type. In this case, the 32-bit integer data type is considered to be simpler than the 64-bit floating point representation for float64. So all of these values are converted to floating point, and each one of these things, if I ask for its type, is numpy.float64. All right, so this can cause some nasty surprises if you aren't expecting it, or even if you are expecting it and you forget. For example, let me show a different example here. If I say something like this, what variable names am I using here? Okay, it looks like I'm reusing some names, so let me just create A5 here. If I say A5 gets np.array 3, 4.5, 6.789. Now here, this final value in this list of an int and a float, this value is a stir, and NumPy will convert everything to a stir. So A5 now contains an array of 3 stir values. And dtype is an indication of what the data type of these values is. This coding here, U32, means that these are encoded in a Unicode character set. Alrighty, let's take a look now at operations that we can do on lists. I mean, we're familiar with these. Oh, I accidentally still have 1234 to the 1234 power as the first value in ls1, so let me correct that by saying ls1 sub 0 gets a 0, which is what we used to have. There we go. And we know that for lists, the multiplication symbol means repetition. So if I say ls1 times gets 2, this is the same as saying ls1 gets ls1 times 2, which in turn is the same as saying ls1 gets ls1 plus ls1. All right, so the multiplication symbol here is doing a repetition, and the repetition in turn gets converted into a concatenation of multiple copies. All right, and so now ls1 contains the 10 values, 0 through 4 followed by 0 through 4 again. If I try to say plus gets 1 on my list, well, this is not valid because it's attempting to do ls1 gets ls1 plus 1, and the plus symbol is not defined between a list and an ordinary int. You can use plus to concatenate two lists together, and you can use plus to add two ints together, but for a list plus an int, that operation is not defined, and so I just get an error. On the other hand, as I actually just mentioned, if you have lists on both sides of the plus, then it is treated as concatenation. All right, so for lists, the times symbol, the star symbol, and the plus symbol are interpreted as repetition and concatenation, whereas for ND arrays, they are interpreted as mathematical operations, vector-oriented mathematical operations. All right, so here's my ND array A1, and if I say A1 times gets 2, this is a scalar multiplication into an array, and what I get won't be surprising. Each of the items within A1 has been multiplied by 2. Similarly, if I say A1 plus gets 1, this is a scalar addition, and each of the items in A1 has 1 added to it. So now I have 1, 3, 5, 7, 9. And if I add these two, if I add A1 to itself, this is done as a vector sum, and the upshot is that the result has each of the values that A1 currently has, but they're all doubled. All right, so I've got 2, 6, 10, 14, 18. Now, I do want to point out that this doesn't actually change A1 because there's no assignment operator in that addition statement. So A1 is actually unchanged. But if I compute A1 plus A1, that returns an ND array containing 2, 6, 10, 14, 18. Okay. We can use slicing in ND arrays, just as we can within lists or tuples. However, a slice within an ND array is not a separate copy of a part of a list or a part of a tuple. A slice is a view, like sort of a window or a view on an underlying part of the ND array. So let's see what I mean by this. I'm going to create A2 to be a wider ND array than A1. A2 contains these values from 0 through 10. If I use a slice, 2:6, this does mean to retrieve the values in A2 from item sub 2 up to but not including item sub 6. So in other words, here we have item sub 2, 3, 4, 5, but not including 6. So that is the slice that we will observe. But that's not a separate copy. And what I mean by that is if I say A2 sub 2:6 gets -8, then each of these values in the slice, each of these values in this view on A2 is going to be changed, to -8. So A2 is directly modified, and each of the values in that slice has been changed to -8 by doing that assignment. If I don't want a view and I do want a separate copy, then I do have to use the .copy method of the ND array. All right, so here's my A2. Did I miss something? Ha! Interesting. So I apparently deleted an example going from slide 46 to slide 47 here. But that's all right. We'll fix it up here. So I have a -24 in the sub 2 position. So I'm assuming that what got deleted here was an A2 sub 2 times gets 3. All right, so that now A2 has a -24 in the sub 2 slot rather than a -8. And let's suppose that I want a copy of these first 5 values, that is, values sub 0 up to but not including sub 5. Sub 5 is actually the final 8 there. Here I'm saying A4 gets A2 sub :5 .copy. All right, so there's A4, here's A2, and if I modify A4 now by multiplying by -1, this does change A4, but it does not change A2. Okay, so A4 now contains -1, well, 0 first, and then -1, and then positive 2488 instead of negative 24, -8, -8. But A2 is unaffected because A4 is a completely independent copy. All right. Well, so I claimed that an ND array is an n-dimensional array. So far, the ND arrays that we've looked at have all been one-dimensional arrays of either integer or floating point values. If I want to create an n-dimensional array, then I can do that using an iterable on iterables. For example, I can use a list of lists, or a list of tuples, or a tuple of lists, or a tuple of tuples if I wanted to create a three-dimensional ND array. This particular example here is creating an ND array that is two-dimensional. It has 2 rows, and each of those 2 rows has 4 columns. Now, it is necessary for an ND array to have full, complete rows and columns. You can't create an ND array that has 4 items in the first row and 2 items in the next row. They have to be all the same dimension. So let's do this. A1 gets np.array, and I'm going to use a list of lists. 1, 2, 3, 4 is my first list, and my second list is 6, 4, 2, 0. All right, so there's my list of lists, and here's my closing paren on my creation function. And there we are. So now I have a two-dimensional array. I can query the array to find out what its dimensionality is by saying array.ndim, number of dimensions. All right, so I get told that it's two-dimensional. And I can find out the specific number of rows and columns by requesting the shape of the ND array. Shape always gives me back a tuple, showing me how many items there are in each dimension of the array. Now, A2, we still have A2 from back up here, and A2 is one-dimensional. All right, remember, here is A2. If I ask for A2.ndim, I'm going to get 1. And if I ask for A2.shape, I get a one-tuple. Okay, it's still a tuple, but it's a one-tuple here, telling me that there are 10 items within this ND array object A2. Now, another way of creating a multidimensional ND array is to start with a one-dimensional ND array and then reshape the array with the reshape function. So that's what's going on in this example on slide 49. I'm going to start out with A2 being an ND array created from A range 12, so that's going to be the values 0 through 11. And then I'm going to create A3 by taking A2 and reshaping it to have 3 rows and 4 columns. All right, so A2 has not been changed by this. A2 is what it was before, but A3 now has 3 rows and 4 columns, and consequently A3.ndim is going to be 2, and A3.shape is going to be 3, 4. All right. There are many other pre-specified functions, methods that you can use for building various special kinds of ND arrays. For example, np.ones builds an ND array of all ones. Now the shape here that you give as an argument is a tuple. So let's suppose I want 5 rows and 6 columns. There we are. And by default, notice that I get float values, or technically float 64 values in that array of ones. I can also create an array of zeros. I can create an array of some arbitrary value by using np.full. np.full takes a shape as its first argument, let's say 3 rows and 7 columns, and then a value, let's say 1.3, who cares? as what you want to have fill in all of the elements in the multi-dimensional array that you're creating. And then we have two ways of creating identity matrices, depending on which one you remember first. We can say np.I, let's say 5, so this would be a 5 by 5 identity, or np.identity 5 does exactly the same thing. Okay. Now, we looked at the idea of getting slices from a one-dimensional array. If I look at A2, of course, I've changed A2 now to contain the sequence of values from 0 through 11. But recall that if I say A2 sub 4:8, that this is a view on part of A2. The same thing is true in multidimensional arrays. I can also get slices of multidimensional arrays, and those are likewise views. So let me create this array of 3 rows and 5 columns. I'm going to copy and paste this code from slide 51. Okay, get that over here. All right, and so now I have A1 modified to have 3 rows, 5 columns, multiples of 2 in the first row, odd numbers in the second row, and then decreasing -5 to -1 in the third row. Nothing important about the numbers, they're just easy to see, basically. And if I say A1 sub 3,5, let's say, actually that isn't going to be in the array. Sorry, I've been doing R programming this morning. Let's convert back to Python. 2,4. Okay, so A1 sub 2 is going to be the sub 2 row, and A1 sub 2, 4 is going to be the sub 4 item. So that should be the -1 in row sub 2, column sub 4. But I can use slices in both dimensions. So if I say A1 sub 1 colon, comma, colon 3, what that means is show me the slice of rows starting from row sub 1. So I'm going to get row sub 1 and row sub 2 for the row slice, and show me the columns up to but not including 3. All right, so I'm going to get the sub 0, 1, and 2 items from row 1, and the sub 0, 1, and 2 items from row 2, row sub 2. And this again is a view. So if I assign some new values to this, here I'm multiplying each value in there by -3, that is going to affect A1. Okay? All of these 6 values in the lower left quadrant, if you will, it's not quite a quadrant, but close to, of A1 have been multiplied by -3. All right, now A1 with one subscript gets me a particular row. So that's going to give me row sub 2, which will be a one-dimensional ND array. Okay, so A1 is two-dimensional, and A1's shape is 3 by 5. A1 sub 2, on the other hand, is one-dimensional, and its shape is 5 values. Okay, so its shape is a one-tuple, showing that it just contains 5 values in it. Okay, now I can use the notation A1 sub 2 comma 1, that is row comma column. As an alternative, I can also just ask for the row 2, and within that row, the column sub 1, and assign a 5 there. And this does index this particular value within the array A1. So it's A1 sub 2 is the sub 2 row, the third row. A1 sub 2 sub 1 is the sub 1 item, the second item of that row. And so this also does end up modifying A1. An alternate, slightly more long-winded way of accomplishing the same thing, of just getting a row. Here I've said give me row sub 2, and that works fine. But if I want to be more explicit that this thing is a two-dimensional array from which I want all of the columns of one row, I can specify colon as my range. Remember that colon all by itself is simply a shorthand for 0 colon n, where n is the number of items in that column in this case. Okay, so in other words, we could say A1 sub 2 comma 0 colon 5, since there are 5 columns in each of these rows. So we're saying from column 0 up to, but not including column sub 5. And there we are. Okay, now since this is only one row, if we ask for its shape, we're going to get a one tuple telling us how many items there are in the row. Likewise, if we ask for its dimension, .ndim, we're going to get back a 1. Now, sometimes you will find yourself with a vector, a one-dimensional sequence of values, and you need to call some function in some module that you're trying to use that expects you to provide a two-dimensional ND array. And the question is then, how can you take your one-dimensional vector and pretend that that thing is a two-dimensional array? This is not so outlandish as it sounds. I mean, if we're doing matrix computations, you can have a 1 by 5 matrix or a 5 by 1 matrix and think of those as distinct from 5-item vectors. In Python, what we're going to do here is to use an extra set of square brackets. Recall that I said that if we used a list of lists, we could get a two-dimensional ND array when we do our construction. So here is A1. And if I extract from A1, instead of extracting just row 2, let me extract rows 2 up to but not including the end. Well, now this seems strange because row sub 2 is the last item, the last row in the array. But still, when you ask for a slice, you will get a slice even if there's only one item in the slice. And therefore, this thing is an array of one item which has 5 columns in it. In other words, the shape of this thing is 1 by 5, and the dimensions are 2. So this is a two-dimensional thing of one row and 5 columns. And if I ask for, if I use the column dimension as well with the second colon, I get the same result. All right, so that's a two-dimensional array, 1 row and 5 columns. In this next example, we're asking for all rows by just using colon in the row index, and we're asking for a slice of columns. So A1 sub colon comma colon 2. Let's take a look at what that means. That means, come here, there we go. Okay, got my closing bracket in there. So all rows means that we're going to get every row from A1, but we're only going to get columns starting from column 0 up to but not including column 2. So we're going to get columns 0 and 1 of each row. All right, so we're going to end up with those 6 values, which is an array of 3 arrays of 2 items, which of course we can check the shape and the dimension if we don't happen to believe that for whatever reason. So it's 3 rows, 2 columns, and of course it's two-dimensional. All right, now let's suppose that we want to get just a single cell out of this array. Then, and we're focusing on that value minus 15. If we want that value as a scalar, then we can simply use its row and column as indexes, and we will get that scalar result. This is not an array, and if I try to ask for its number of dimensions, it doesn't, it's dimensionless. And if I try to ask for its shape, okay, it's shapeless. Okay, it's a scalar does not have a positive dimension and does not have any notion of rows and columns. But what if I needed to treat this single value as a vector of one item or as an array of 1 row and 1 column? Okay, I can treat this value minus 15 as a scalar or as a vector or as a two-dimensional array. And the trick is to just use slices. All right, so instead of saying A1 sub 1, what I'll do is I'll say A1 sub 1 colon 2. All right, now let's think about that. That means from row 1 up to but not including row 2. Well, clearly that's just 1 row, but because it's a slice, it's treated as a it's treated as a dimensional thing rather than just a scalar thing. So this time I have it's called an array, but since it's only got 1 dimension, it's really a vector containing the minus 15. And if I do the same trick for both the rows and the columns, now I have a two-dimensional array with 1 row and 1 column. And let's just check that to be sure. So I'll ask for the endim, and sure enough it's two-dimensional. And I'll ask for the shape, and it's 1 by 1. All right, well that's a trick that you don't often have to know, but on the other hand, it's an extremely useful thing to understand about the distinctions between individual subscripts and slices. All right, all of that stuff involved using integer indexes and slices as indexes for sequences of rows or sequences of columns. Another way that we can access certain parts of an ND array is to use what's called Boolean indexes, which are true and false values. So let's illustrate what we're talking about here. All right, just let me redisplay A1 for a reminder. And I'm going to create this vector called B rows, which is a Boolean vector to specify the rows that I would like to get from my array A1. With slices, with slice notation, you know, 1 colon 2, 1 colon 3, 0 colon 4, what have you, I can only get a sequence of rows. I can't get, well, I want row number 5, I want row number 7, I want row number 13, but I don't want any of the other rows. Now, a Boolean index, on the other hand, does allow me to specify individual rows that I want by using true as my row selector in my Boolean index. And I can specify rows that I want to leave out with false. Okay, so this is, I know it looks like browse, but I promise it's B rows. It's my Boolean rows vector. And if I use that as an index into A1, okay, since I've used B rows as the first index, it's going to be indexing on the rows, and I'm going to end up getting just the first row and the third row. And the middle row is left out of what I get back from A1 sub B rows. Like slices, a Boolean index gives me a view on the underlying part of the two-dimensional ND array. So if I say A1 sub B rows times gets a -1, well, I'm just converting all the values in row 1 and in row, well, I'm sorry, row sub 0, and row sub 2. I'm converting all the values in those two rows to their negatives. Okay, so I started out with 0, 2, 4, 6, 8 in the first row. Now I have 0, -2, -4, -6, -8. Similarly for the sub 2 row as well. And just as I used a Boolean index of 3 values to specify that I want certain rows but not other rows, I can also use a Boolean index in the columns to indicate which columns I want. And here, because I want all rows, I've used colon to specify, the slice notation, colon, to specify that I want all of the rows, but in this case only certain columns. I'm going to get the sub 0 column and the sub 3 column, but not the other columns. Now let me copy and paste this thing because I'm much too lazy to type it all in. And we'll confirm that we get what is shown. Okay. All right, so from A1, we're going to get all rows, but only column sub 0 and column sub 3, not the other columns. And there we are. Okay. When you compare an ND array using something like a relational operator or an equality operator, instead of getting back a single true or false value, you actually get back an ND array that's the same shape as the original ND array, in this case A1, but in which we have true or false values on an element-by-element basis depending on the relationship, depending on whether the relationship was true or false. All right, so here's my A1, and if I say A1 less than -5, this relational test is performed item by item. So we ask, is 0 less than -5? Well, the result of that test is going to be false. Is -2 less than -5? That's also false. -4 gives us false. But here, for -6 and -8, each of those is less than 5, so we're going to get true values for the comparison there. And continuing on through the other 10 items in this array, what we end up with is a Boolean end array with false and true values on an item-by-item basis, depending on whether this relationship was true or false. Now, I can take that Boolean index, that two-dimensional Boolean index, and use that as an index into A1 itself to give me, in effect, a view on all of the items where the relationship is true. And that allows me, for example, to change all of those items where the relationship is true to some other value. Or I can add a number, or I can multiply by a number, or what have you. All right, so here's my Boolean index. And if I say A1 sub A1 less than minus 5, if I just do this, I get back a one-dimensional end array of all of the values that are less than minus 5. But if I use that instead on the left side of an assignment statement, like gets 8, then each of these values in the two-dimensional array A1 is going to be replaced with an 8. And there we go. So I used to have minus 6, minus 8 up here. Now I have 8, 8 instead. I used to have minus 9, minus 15. Now I have 8, 8. In the third row, I used to have minus 15, and then minus 5, and then minus 9. So the minus 15 and the minus 9 have both been changed to 8s. This gives me a good way of dealing with positive or negative outliers, for example, in an array of values. It turns out that if you want to do logical combinations of equality and inequality tests, and this strikes me as a flaw in the design of the language, but you know, who am I to say? You have to use binary operators rather than the logical named and, or, and not. So we have to use the ampersand symbol for and, the vertical bar symbol for or, and instead of the exclamation mark character, we use instead the tilde symbol, which means to invert. So true becomes false, false becomes true in the case of that operator. A fourth operator that we have is XOR, which means that one side is true and the other side is false, but not both are true. So one is true, but only one is true of the two things being compared. An annoying fact to remember here, furthermore, is that these operators have higher precedence than the equality and relational tests that you're trying to combine them with. So you have to remember to use parentheses around your ands and your ors and your exclusive ors. All right, so I'll show you what I mean here. Here's A1. And we have modified A1, so A1 has a bunch of 8s in it now. I can test whether A1 is greater than 5 and A1 is less than 9. However, the ampersand has higher precedence than the greater than symbol or the less than symbol. So in effect, what this does is A1 greater than 5 and A1, which is less than 9. And that's an invalid test, so I am going to get yelled at for doing this. I need to remember to use the parentheses, as I had said, to force the relational test to be performed before the logical AND is performed. All right, so here I've got A1 greater than 5 in parentheses and A1 less than 9, also in parentheses. All right, and this gives me my Boolean two-dimensional array of true and false values. Now, it turns out this is just kind of an accident, but all of the true values that I'm going to get here are the 8s that I just assigned, and also this one value of 7. 9, of course, is not less than 9, and all the values less than or equal to 5 are not greater than 5. So I only end up getting trues for the 6 8s and the 1 7. All right, so here are the 2 8s in the first row, and then we have 2 8s and a 7 in the second row, and 2 8s in the third row. If I then use that entire expression as an index into A1, I can modify those selected values, the values that are marked true, using some kind of assignment expression. Okay, let me copy that. All right, so A1 sub, and then my relational and logical expression. And this time I'm going to subtract 5 from all of the values that are marked true from that test in A1. And the upshot is that what had been 8s are now 3s. All right, so I've got 6 3s in here now, where I used to have 6 8s. And I've also got 1 2 in here, where I used to have a 7. Okay, so that takes care of using slices as indexes into arrays, which gives us sequential rows or sequential columns, or both, and also binary indexes into arrays, which gives us more flexibility about which individual elements we're going to operate on according to equality and relational and logical comparisons. The third indexing method that we can use to select certain rows and columns and cells out of an array is what's called fancy indexing. Why is it called fancy indexing? Well, I think it's called fancy indexing because the person who dreamed it up ran out of imagination and couldn't think of anything else to call it. Okay, so I'm not sure that fancy actually conveys much about what this is doing, but let's demonstrate the notion of fancy indexing. I'm going to reset A1 so that it doesn't have all these 2s and 3s and stuff in it. Let me copy and paste that thing. All right, so A1 is back to its original form from earlier in the lecture. And there we have it. Now, to do fancy indexing, you use an outer pair of square brackets to do your array subscripting. And then within the square brackets, you write a list of the rows and possibly the columns that you want. So here is my A1 with square brackets. I'm just going to leave the square brackets open here. So I'm indexing something within A1. And the first dimension that I'm indexing is going to be the rows. The second dimension would be the columns. But what I'm saying here with my fancy indexes, the rows I want are row 2 and row 0. Not only can I select individual rows rather than sequences of rows, but with fancy indexing I can even change the order of those rows. So what I'm going to get out from this is row sub 2 followed by row sub 0. The result is going to be an array of 2 rows and 5 columns. But I've got the last row first, and the initial row last. This thing is, as I suggested, a two-dimensional array. Whoops. Didn't mean to type that continuation character. And of course its shape is 2 by 5. Okay, now in this next example, I'm using a colon for the rows. So I'm asking for a slice, which includes all of the rows, but this time I only want certain columns. And I'm going to change the order of the columns that I want. Also, I'm going to duplicate one of the columns. So I'm going to ask for column sub 3 first, followed by column sub 2 and column sub 1, and then a second copy of column sub 2. Okay, so not only am I selecting individual columns that I want, but I'm specifying the order that I want them in, and I'm indicating that I want to have one of the columns duplicated. Okay, so I've got this column, 4, 5, minus 3, 2 times. Okay, that was column sub 2 within A1. Okay, this final example of fancy indexing frankly seems a little inconsistent with the previous examples. Now, in the previous examples, we did fancy indexing on the rows with all the columns. Now, we could have put in here square bracket 2 comma 0 close square bracket comma colon to explicitly indicate all the columns. In the red example, I'm asking for all the rows using the colon for slice notation, and then just certain columns within those rows using the fancy indexing. But if you use both fancy indexing for rows and columns, you might think that you're going to somehow get a subrectangular matrix, but actually what you get here are just individual cells pulled out of the original empty array. So I'm going to get cell sub 0, 0. All right, A1 sub 0, 0 is this 0, so that's the first value that I get. Then I'm going to get the cell 1, 4. Okay, so here's row sub 1, column sub 4 is the 9, so I get that next. Then I'm going to get row 0, column sub 2. All right, row 0, column sub 2 is the 4. And finally, row 2, column sub 0, which is the minus 5. So using fancy indexes for both the row and the column actually just gives me a one-dimensional empty array, a vector, if you will, of individual values where the corresponding row and column values are just kind of matched up with each other. Alrighty, so what have we done? We've looked at how to create empty arrays. We've talked about how empty arrays are implemented in terms of containing all values that are of the same data type and that are guaranteed to be in contiguous memory for highly efficient vectorized computations. And we've looked at several ways of creating empty arrays using various kinds of construction functions, as well as 3 different ways of indexing values within an empty array. We looked at using slices on rows and columns. We looked at using Boolean indexes on rows and columns or on the entire matrix, on the entire two-dimensional array, I should say. And then finally, we've looked at using fancy indexes on either the rows or the columns. There is lots more stuff that Numpy provides that we could easily spend another entire week talking about, but here I've just summarized some of the goodies that are available. We have vectorized versions of all the usual math functions, absolute value, square root, e to the x, log of x, blah, blah. We have a variety of statistical methods, mean, sum, standard deviation, variance, min, max, etc. There are a variety of random number generators for different random number distributions, normal, uniform, on and on. We can do linear algebra calculations, multiplying a matrix times a matrix or a matrix times a vector. We can do solutions of linear equations. We can sort values. We can combine values using set-like operations. And there's a whole family of functions for reading ND arrays in from files or writing ND arrays out to files. In the homework, I'm going to ask you to read some more in the textbook about ND arrays, about Numpy, I should say, to try out some more of these things. Okay, well that is finally it for week 3. Hope you are all doing well. Take care.